Hello everyone, welcome to Dreamers. In this video, we are going to discuss the infinite square well. Here we are discussing in one dimension. A particle in this potential is completely free except at the two ends for x is equal to 0 and x is equal to L, where an infinite force prevents it from escaping. Please note that at x is equal to 0, potential energy is equal to infinity, and for x greater than L, the potential energy is equal to infinity, and for x less than 0, the potential energy is equal to infinity. Again, outside the well, the wave function is equal to 0, but inside the well, the wave function is not equal to 0. The wave function is equal to 0 outside the well because the probability of finding the particle there is 0. So inside the well in one dimension we can write the Schrodinger equation minus h cross square by 2m del square psi by del x square plus v psi is equal to E psi. As inside the well, that is for x greater than 0 and less than L, V is equal to 0. So we can write minus h cross square by 2m del square psi by del x square is equal to E psi, or we can write del square psi by del x square plus 2m by h cross square E psi is equal to 0. Now we have to solve this Schrodinger equation to get the energy eigenvalue as well as the wave function. So we have obtained del square psi by del x square plus 2me by h cross square psi is equal to 0. Let this quantity be equal to k square. So we can write del square psi by del x square plus k square psi is equal to 0, where k is equal to 2me by h cross square. Now the general solution of this Schrodinger equation is similar to the solution of harmonic oscillator, and that is given by a sin kx plus b cos kx. Now we want to find out what are the values of a and b, which we can find out from the boundary condition. We have psi is equal to a sin kx plus b cos kx. From the boundary conditions, we have psi must be 0 at x is equal to 0. We know that at x is equal to 0, sin kx is equal to 0, whereas cos kx is equal to 1. Sin kx is equal to 0 at x is equal to 0, whereas cos kx is equal to 1. So in order to have this, b must be equal to 0. So we can write psi is equal to a sin kx. Again, another boundary condition demands that psi at x is equal to L must be equal to 0. So from this condition we can write that psi at x is equal to L a sin kl is equal to 0. We know that a is not equal to 0, hence we can say that sin kl is equal to 0, or kl is equal to n pi, or k is equal to n pi by L. Please note that k is equal to n pi by L, where n is equal to 1, 2, 3 and so on. So we obtained psi is equal to a sin kx, where k is equal to n pi by L, or we can write a sin n pi x by L. Again, we have to find out what is the value of a, which we can find out from the normalization condition, that is minus infinity to infinity psi star psi dx is equal to 1, or from this we can write a square 0 to L sin square n pi x by L dx is equal to 1. Please note that minus infinity to infinity we can write it as minus infinity to 0 plus 0 to L plus L to infinity, as in this region your wave function is equal to 0, hence we are writing 0 to L. Again, which can be written as a square 0 to L 1 by 2 1 minus cos 2n pi x by L dx is equal to 1. Please note that here we have used the relation cos 2 theta is equal to cos square theta minus sin square theta. Again, we can write cos square theta as 1 minus sin square theta. So finally you will get 1 minus 2 sin square theta. So from this relation you can write that 2 sin square theta is equal to 1 minus cos 2 theta, or you can write sin square theta is equal to 1 by 2 1 minus cos 2 theta. In our case, theta is equal to n pi x by L. So when you integrate this integration, you will obtain x 0 to L minus 1 by 2 L by 2n pi sine 2n pi x by L 0 to L. Please note that at x is equal to L and at x is equal to 0, this term becomes 0. So this quantity must be equal to 1. Again, you can write a square L minus 0 by 2 is equal to 1, or a square is equal to 2 by L, or a is equal to 2 by L root of. So we have obtained psi x is equal to a sine k x, where a is equal to root over of 2 by L and k is equal to n pi by L. As k is function of n, sometimes we may write this is k n. So finally we'll write psi x is equal to 2 by L root over sine n pi x by L, and this is normalized wave function. Please note that here, that is in the range x greater than 0 and less than L, potential energy is equal to 0. Hence, total energy is equal to h cross square kn square by 2m. That is nothing but kinetic energy. We know that kinetic energy is equal to p square by 2m, as p is equal to h cross k, hence you can write h cross kn square by 2m, which is equal to h cross square kn square by 2m, where m is the mass of the particle. Again, we can write h cross square by 2m. We know that kn is equal to n pi by L, so whole square, and finally we obtain En is equal to h cross square by 2m n square pi square by L square. So this is the expression of energy. This is the expression of energy. So let's have a quick summary. Whatever we have read, we have read that at x is equal to 0, potential energy is infinite, and at x is equal to L, potential energy is infinite. For x less than 0, potential energy is infinite and wave function is equal to 0. For x greater than L, potential energy is infinite and wave function is equal to 0. That is, the probability of finding the particle is 0. For x in between 0 to L, potential energy is equal to 0, whereas psi is not equal to 0. Please note that here psi is a function of x, and we are discussing one-dimensional infinite square well potential. We know that the Schrödinger equation can be written like this: H potential energy is equal to 0, hence we'll write this. Again, multiplying both sides, minus 2m by h cross square, we will get this expression where k square is equal to 2me by h cross square root over. The general solution of this equation is psi x is equal to a sin kx plus b cos kx. If we put the value of k, it will look like this. Again, from the boundary condition, we have found out that value of b is equal to 0 and hence psi x is equal to a sin kx. Again, from the boundary condition, we can see that the value of k is equal to n pi by l, that is at x is equal to l, psi x must be go to 0, and from this condition we obtain this, and finally we obtain the energy to be equal to n square pi square h cross square by 2 ml square, where n is equal to 1, 2 and 3. Again, from the normalization condition, we obtain a is equal to root over of 2 by l, and finally we have the wave function in this form. Now, so we have obtained the wave function, that is psi n is equal to root over of 2 by l sin n pi x by l, and En is equal to n square by square h plus square by 2 ml square. The length is L. So from this we can write for n is equal to 1, E1 is equal to pi square h cross square by 2 ml square. Please note that H energy is function of n, so we are writing here En. Similarly, psi n. For this case, wave function will be equal to root over of 2 by L sin pi x by L, sin pi x by L. And if you plot the wave function, it will be like this. Okay, it will toss this end to this end. Now, for n is equal to 2, please note that from this energy relation we can write En is equal to n square E1. So it will be E2 will be 4E1 and wave function will be equal to root over of 2 by L sin 2 pi x by L. Please note that psi 2, so here 2, psi n here n, psi 1 here 1. So the wave function will be looks like this. So it will end it at this point. Okay, so it will end at this point. Your function will look like this. Okay, your function will look for psi 1 like this, for psi 2 like this. Now, for n is equal to 3, E3 will be equal to 9E1 and the wave function will be root over of 2 by L sin 3 pi x by L and so on. So the wave function will look somehow like this. Now please note that here, if you will see that psi1 has no node. Psi1 has no node. We are not counting the endpoint as a node. So psi1 has no node, psi2 has one node, and psi3 has two node. So number of node is equal to n minus 1. Number of node is equal to n minus 1. So please note that as you go up in energy, each successive state has one more node. Here number of node 0, 1, 2 and so on. More. Again, so we have seen that for n is equal to 1, the wave function looks like this. For n is equal to 2, the wave function looks like this. For n is equal to 3, the wave function looks like this. This is x is equal to 0, x is equal to L, and this is x is equal to L by 2. That is center of the well. This is psi 1, psi 2 and psi 3. Please note that psi 1 is even, psi 2 is odd, and psi 3 is even with respect to center of the well. Center of the well. In order to demonstrate this, some authors center the walls at origin. That is, they consider x is equal to minus a. The origin they put x is equal to 0, and here they took plus a. Okay, so in that case, what they will find, the even functions are cosine and the odd functions are sines. Okay, this is very important. Now we discuss about even and odd functions. Next, we have discussed regarding number of node, that is number of nodes, which is equal to n minus 1. Next important property is that psi m star psi n dx is equal to delta m n, that is from 0 to L, where delta mn is known as Kronecker delta function. Kronecker delta function. What is this? This Kronecker delta function is equal to 1 for m is equal to n, and this is equal to 0 for m not equal to n. So we say that the wave functions are orthonormal. Again, if you consider another point, you can write that they are complete. They are complete. They are complete in the sense that any other function, any other function can be expressed as linear combination of this psi and x. So we can say that they are complete. Thank you.